Hi, everyone. As you're joining today, please let us know where you're tuning in from. Perfect. We are live on LinkedIn, and let me just check over on YouTube. Perfect. We are now live on all channels. Welcome, everyone, to this month's Delta Lake Community Meetup. My name is Carly Akerley, and I am a communications manager at the Linux Foundation. Wherever you're tuning in from, let us know in the comments below. We are streaming through Zoom to LinkedIn and YouTube. We will be taking questions throughout the session, but holding off on answering towards the end. We have an awesome agenda lined up for you today. We'll be diving into the latest features and improvements in Delta Lake 3.2, exploring the integration with Pandas and discussing what the future holds for Delta Lake. So to get things kicked off today, we will turn it over to Matt Powers. And Matt, you have slide control.
Wonderful. Hi, everybody. My name is Matthew Powers. I'm a developer advocate at Databricks, and I'm going to be chatting about Delta Lake and Pandas. So I don't have those little arrows that I had in the past to do my slide control, Carly. So we will just do, yeah, next slide. Perfect. Okay, here are the features so this is going to be just a quick chat, 10 minutes about Delta Lake and Pandas and why Delta Lake is amazing for Pandas. We're going to be chatting about a few different great features. First off, reliable transactions, amazing, fundamental, you need them. We'll talk about time travel, why that's great for the Pandas community. We will also talk about schema enforcement, how that helps keep your Delta tables pristine, as well as constraints, which keep the rows of your tables to make sure that you're not violating any constraints that are not acceptable. We'll talk about how you can overwrite partitions of a Delta table, which is really useful for Pandas community because that actually doesn't exist in any other Pandas engine lakehouse storage system combination. And we'll talk about performance optimizations. Next slide, please. Perfect. So let's take a look at how to create a Delta table with Pandas. So on the left-hand side of the slide deck, we can see we are instantiating a Pandas data frame that has 3 rows of data, 1, 2, and 3, and a single column X. And then we're using that write Delta Lake function, which is defined in Python Delta Lake, aka Delta RS. And that is going to append the Delta table to the Delta table. And then we are going to just read in that Delta table and to a Pandas data frame just to make sure that that's all working properly. So once we have that Delta table created, we can see we can easily append to the Delta table. So we instantiate a second Pandas data frame, and then we use that same write Delta Lake function. But in this time, we're going to set the save mode to append, and that's going to make it so that we can just append this existing table. So after we create and append to the Delta table, we can see that we just have this single table with a column X and the values 1, 2, 3 from the initial creation and 9, 8, 10 from the append operation. Next slide, please.
Yes, and Matt, I think I have the solution to why you can't advance. So one moment.
Give me control.
Yes. 1 second. Okay. How about now, Matt?
Yeah, I got it. All right, so let's take a look at overriding the Delta table. And this is a different type of transaction. So we're instantiating a third Pandas data frame. It has a single column X with three rows of values, 55, 66, and 77. We're using that same right Delta Lake function, but now we're setting the mode, the save mode parameter to overwrite, and that's going to overwrite the existing table. So now it kind of removes all of the existing data and it adds this new data. That's what an overwrite operation does. Now, all of these operations until now are transactions with the ACID properties. We don't have enough time to go into that in too much detail, but basically those are reliable transactions like you would get from a database. You don't get reliable transactions if you're using data lakes or CSV files or Parquet files or whatever. Okay, let's look at our Delta table, the three different versions, and how we can time travel between these different versions. So version 0 of our table has three rows of data, 1, 2, and 3. Version 1 of our table has those three rows of data, 1, 2, and 3, but in addition, 8, 9, and 10. That was the data we appended. And version 2 just has 55, 66, and 77. So now we can see in the lower left-hand portion of the slide, we're reading in the Delta table and we're setting the version parameter 0. And we can see that we can still access version 0 of the data. Now that's really handy and really cool. Of course, you don't get this sort of time travel functionality if you're using a data lake. This is Delta Lake specific, and it's very nice. Now, one thing that you might be surprised about and be like, wow, that's surprising. I'm surprised I can still access that data. I thought I overwrote this data. And that's a great question. So Delta table operations are logical operations. So when you append to a table or overwrite a table or you perform a transaction that's going to be removing data, it's just removing it logically. It's not physically deleting the data from disk. You need to perform a vacuum operation if you want to physically remove stuff from disk. So now you can turn your attention to the lower right side of the slide. We can see that if we read in the Delta table and we don't set the version parameter, it's just going to read the latest version by default. So this is very nice. I think one of my favorite things about time travel and version data is like when you make a mistake, you can undo it and then restore to a previous version of your Delta table. Okay, let's look at schema enforcement and how this benefits the Pandas community. So let's look at fourth Pandas data frame. This Pandas data frame just has a single column Y with two rows of value, 111 and 222. Now, when we try to use this right Delta Lake function and append this Pandas data frame to a Delta table with the save mode set to append, we can see that this is rejected. And we're getting this value error. Schema of data does not match table schema. Now, this is great. So this schema doesn't match our existing Delta table. So Delta's saying, hey, the schema is different. We're rejecting this append. Now, of course, data lakes have no such checks, so they're easily corruptible. So this is really nice how Delta tables have this kind of built-in schema enforcement. Now you can bypass the schema enforcement with schema evolution. We're not going to talk about that today, but
Uh-oh, I think we have a frozen mat.
Yes, a frozen mat. Oh no. The world cannot know about pandas now anymore.
Eee. Matt will be rejoining shortly. Thank you, everyone, for your patience.
Yeah, let's wait a couple of more minutes before we take any drastic actions.
Yes, he will show up again, no worries, from Imad in the chat. Yes, he'll be back. We could always as well go out of order and advance to another section while Matt's joining, whatever you think is best.
Yeah. Let me see. How many slides? Oh, he just had 3 more slides. Oh, it's so sad to switch out.
What a cliffhanger.
Yeah. Maybe we should switch out. We can start the type widening
Sure,
and we can resume
All right,
Panda.
let me
Sure.
grab the spotlight then.
Yes.
All right, Joe.
Right, hi.
You're up.
My name is Joan Las Peras. I'm based in Berlin, Germany, and I'm here today to talk about a new feature that's going to be released, that's being released in preview in Delta 3.2, and that's type widening. So I'm going to go over what the feature is, what it's used for, and we'll have a quick look at the end into how it's implemented. So I have a last slide that's a bit more technical. But let's start with a few use cases to get some context about why users may want to apply a type change on an existing Delta table. So 2 fairly common scenarios is, for example, you are storing an ID into your table. You created your table thinking that an integer would be enough, 32 bits would be enough to store that ID. But you've had a lot of orders, a lot of updates on your table, and suddenly overflowing the 32 bits that your integer column can store. And you want to expand that to 64 bits to be able to have more than the number of records that you have. And this is the case where you would want to essentially extend the size of the integer type that you're using. Another example that I have is you have your pipeline that's ingesting data into your Delta table. And the source that you're ingesting from was using a decimal type, for example, decimal precision 12 scale 2. But you want to add a new source, and that source is actually using a different decimal type. And now you're a bit blocked because you need to reconcile these 2 types, and that basically means changing the type of the delta of the column in the Delta table that you're ingesting to pick a decimal type that's wider and can accommodate the 2 others. And if you don't do that, your ingestion is going to fail, and you won't be able to ingest data from the new source until you update the type. Now, how would that work in today's world before Delta 3.2 to change the type on a table? There's no built-in support. That means you essentially have to roll out your own. The documentation gives an example of how you could do that, but it's basically fully rewriting your table. So you rewrite the data, you overwrite the schema, and sure, you can do it, but it's an expensive operation. If your table is very large, if you have terabytes of data, then you need to rewrite the whole data. So that's going to be both expensive and slow. But the main issue is actually if you have any load on your table, if you have concurrent write, then it's very unlikely that this will succeed because this is an operation that will update the table schema. So it will conflict with any other operation that writes to the table. And given the fact that if your table is large, this may take hours to rewrite the data. Any write that happen in the meantime is going to make this operation fail. And unless you explicitly go and tell all your writers to that table to stop writing, this is going to fail, and you won't be able to get through with that manual type change. So this is setting a bit the stage for the feature. And type widening is aiming to make changing types a lot easier for Delta tables. The way it works is you first enable the feature on your table by setting a table property. And this is going to guard against older client versions that don't support that feature and that won't be able to read the table after you change the type. So this is the first step. You enable type widening. And after that, you can change a column type to a wider type using the alter table, alter column command. So this is a simple operation and it actually doesn't rewrite the underlying data. So this is almost immediate. It's only update the table schema. So there's basically no cost in rewriting the data since you're not rewriting any files. And it's also super fast. That means that it won't conflict with concurrent operations that you have on your table. So this is one way, manually changing the type via the alter table command. But you have a second way where you can change the type on your table, and that is with schema evolution. So this feature is integrated with schema evolution. That means that whenever you enable schema evolution on an ingestion operation that you run on the table, whether that is merge into or insert it to, then any type change that you have in your source will be eligible to be propagated to your target table. So in the example that you had at the beginning, you're adding a new source that you're ingesting from that is using a wider decimal type. Then if you have schema evolution enabled, we will allow widening the decimal type in your target table so that it can accommodate the values that you're ingesting from in the source. And this is in the spirit of schema evolution, where you're essentially telling the system, I want to be hands-off. I want schema update to be handled automatically for me without failing my ingestion pipeline. And this is a case where with Delta 3.2, Delta can now reconcile type changes and propagate them through the ingestion pipeline. All right. So quickly covering the different type changes that are supported. Currently, the feature is in preview in Delta 3.2, and it's a limited preview that only supports changing type from byte to short to integer. And the reason for that is that it actually relies pretty heavily on changes to Spark that are going to be released in Spark 4.0, and we essentially need to wait to this change to learn to be able to support the other types. But soon enough, we'll have a Delta 4.0 preview, and then in Delta 4.0, we'll have the full list of type changes supported, which are widening type changes. And you have the list here on this slide. The core type changes are supported both for the manual type change via alter table and using schema evolution. And there are some type changes that are only possible to apply manually. And these are the ones that cross some type family boundary, for example, from integer to double, from integer to decimal, where it's not always clear that we should apply these type changes automatically for the user. And so we want to be careful, and these are only going to be applied if the user explicitly say, I want to have this type change. All right. And then quick peek at the implementation. So this is the more technical slide to understand a bit how this feature is implemented. And we're going to go through the life cycle of a type change from the time you apply it on the table to the time where it's the table is fully consistent with the new type. So what happens essentially when you run the alter table alter column command, this is a very simple operation that just updates the table schema. So there's no modification to the data file. It creates a new version of the Delta table where the type of the column changes from, in this example, integer to long. The file remains the same. And once you've done that, then you can do further operation on your table afterwards. For example, you can insert more values. And any of these new operations is going to be using the new type. So any data that's being written into files after the type change was applied is going to use, in this example, long instead of integer. And the way this works is you now have a table that has a mix of files that have different types. And this is what was not possible before. It wasn't supported before essentially Delta 2.2 and for the type changes at Delta 4.0. This is being able to reconcile all these different types on read. And the way this is done is relying pretty heavily on the packet readers that are in Spark for the Spark implementation, which is reading the packet file with the individual types that are in there, integer, long, and the packet reader is responsible in here to reconcile the type and surface it as the type that is actually in the table schema. So each value is going to be converted from integer to long when needed, so that all the values at the output of the packet reader are long values, and then Spark can consume that. The last point is there's something very convenient with this feature. That is that any ongoing operation after the type change that runs on the table is essentially going to heal the table in a way where, for example, if you start compacting files, you take file 2, file 1, file 2, file 3 together and compact it into a new file, then this new file is going to use the new type. And you see that files that are using the old types are slowly going to disappear from the table as you update values in them, you write them, you compact them, so that eventually you will have very few or no file that use the old type. And you essentially got your table rewrite for free just with daily ongoing operations that you do on your table. And this is where you can, at this point, drop the feature and your table is not fully using the long type. Yeah, that's all I had for you today. And we can take I can take more questions at the end of the session.
Awesome. Thank you so much. Perfect. Welcome back, Matt. Hello. I didn't see you pop in there.
I'm back.
Woo.
Wi-Fi hotspot in New York City right now, but apparently New York City doesn't have internet. I don't know.
Awesome. Well, Arun, would you like to present your section now? And then Matt, if you want to finish up yours, maybe at the end of the session, does that sound good?
Yeah. Hotspot presenting. Love it.
Or we can just leave it for a Q&A, whatever you're most comfortable with. Awesome. So Arun, you now have slide control.
Yeah. Hi, everyone. I'm Arun. I'm joining from Singapore. I work for a company called Grab. We are an everyday app based out of Southeast Asia. Today I'll be speaking about improving backbone performance in Delta Lake 3.2 and how we ended up contributing this feature. So this feature actually uses inventory reports from a cloud provider. So basically, I will take you through how we use inventory in general at Grab. Then what is the use of Delta Lake in Grab, and then how we ended up developing this feature and contributing it back. So today we use AWS S3 inventory reports to do storage observability, usage observability, and things like that. So we are able to identify how much a table costs and how is the file distribution inside the table in terms of size. And then we are also able to identify using access logs, like how the data is transitioning between various storage tiers, etc. So, and also identify which particular platform or query, etc. is triggering these transition and movement. So this is how we set up. And then we have these beautiful dashboards to nudge users to either do compaction or optimize, right? Or sometimes even change the query that they are writing. To build these inventory dashboards and insights, we use obviously the inventory reports from AWS, and then we use access logs. So to process access logs, we use oops, I am unable to. Okay, yeah, it's fine. So sorry, I think we skipped. Okay, so we store S3 access logs in the form of a Delta Lake table. So generally, there are analytics data warehouses that use Delta Lake format, and then the security data lake and SIEM solution, which also relies on a Delta format. So S3 server logs are ingested as part of the security operations. So we rely on them to build those beautiful dashboards. One thing across all these different personas, there are few challenges that they face when they run or when they use Delta Lake. So especially within analytics data warehouse teams, there are certain teams that have their own data engineers, scientists, and analysts who are familiar with Spark, Trino, and Airflow. So they kind of do everything on their own. Then there are some low-code users who use managed platform to build their Delta table, and the ETL pipeline health, etc. And the table health are actually managed by the platform team itself. So they just come to our system, they write some random SQL logic, and then everything else is managed by the platform team. For security analysts, we have like our central data engineering team. We help them build the security data lake, the bronze and silver layers, and then they analyze the data on using the applications of their choice. So this is how Delta Lake setup is. We have like around more than 10K Delta tables. So it's a big footprint out there. So when we talk to these different people, and especially the platform team, one thing that they call out about Delta is, yeah, Delta is all good, but when it comes to maintenance job, especially on the platform side, and those platform teams, they find it really hard to decide when to run vacuum. How to nudge users to use optimization techniques, as well as frequently run vacuum when necessary to get best of cost and to not have performance degradation, etc. So there was this interesting conversation where we are like, we have these beautiful dashboards, and we know and we are as part of the platform team, we nudge users to run this optimization or cleanup or when required. Then why don't we just run it for them, right? Like why just nudge them and then wait for them to run? And when we ask them to run vacuum, they would come back and say that it takes a lot of time, so we don't know, maybe we'll do it later. So like all those conversation ended up with like the need to improve the vacuum performance. So we decided that since we have the inventory logs and all the other information readily available, we decided to spend time to understand why vacuum is taking a bit longer to complete for large tables. So first step is obviously identifying the problem, right? So a traditional vacuum algorithm has 3 stages. So it does a recursive file listing. The listing parallelism is like tightly coupled with how your partition structure is, or actually the folder structure inside the Delta table. So the top 2 directories, like how many directories are available in the first 2 levels, in a way control how many listing processes are run. So we want to figure out a way to improve the listing process. So like at first we tried reducing the number of listing APIs. So when a Delta table is in the lakehouse for a long time, and it gets updates only for the recent partitions, right? So there is no point doing a listing for older partition. So this definitely reduces the number of list operations that we do, and thereby reduces the time and cost. So initially we tried building this feature. We rolled it out to few users, and immediate feedback that we got was, it is faster, but there is extra management overhead now, because I need to track the history of when I did cleanup, what all partitions were part of those cleanup, and things like that. The other problem that users raised is basically not all features of Delta Lake sits well with this partition pruning approach, because for example, if you have a random prefix table, etc., it breaks the concept of how we were doing partition pruning. That's when this inventory thing came back to our discussion table. We are like, okay, we have the table that has all the files in S3. Then why not just feed it into the vacuum process, right? So that's when we started working on inventory-based vacuum. So the idea is very simple. We have S3 inventory data in a Delta table. We skip the recursive listing process. We will feed the data from the inventory table into the vacuum process, and then identify which all tables are there for deletion, and then do a parallel delete operation, right? So it will be like a select metadata from inventory table, then apply the retention filters, you get the resultant files. Then you identify which all files are not actively referenced using an anti-join on the transaction log, and then issue the parallel delete operation. So it's very simple. It's very easy to enforce, because we don't have to retain any operational metadata on our side, like when I did last vacuum and things like that. And the algorithm is in line with the legacy or the older way of doing vacuum. So if you want to use this, what is the performance that we observed, right? Like, so before using this, before using this feature, we were like this particular table, like this particular graph shows vacuuming of like before it's single table, after it's multiple tables. So before, like we tried reducing the number of file sizes by actively running compaction jobs for a very large table. So this particular table daily partition volume is 2 terabytes of data. So it's basically processing S3 server logs, and we have like hundreds of S3 buckets, right? So despite all the effort for optimizing and reducing the number of files, our vacuum performance was always like around 30 minutes because it has that many number of files. So after using inventory-based vacuum, now we don't really have to run it for one table. We can run multiple tables in a single application, in a single Spark application. So the right side graph shows that like we can run vacuum within less than 5 minutes for every large table out there. And then, everything ends in like 10-20 minutes for us. So it's a significant improvement. And the number of jobs that we kept using for managing big tables reduced drastically. So we use the optimized write from Delta 3.1, and then we use inventory vacuum to run vacuum whenever needed. So to use this feature, it's very simple. We have introduced a keyword called inventory. So you can use inventory keyword and then pass in either a subquery, or you can pass a Delta table with your inventory information. And then that's just just like old vacuum command. Yep.
Awesome. Thank you so much, Arun. TD, I'm going to pass slide control your way right now.
All right. So actually, before I get into this, because it might be better for Matt to finish up the stuff. This is like more forward-looking updates. I have a very short section. So
Sure thing. Let's go back to Matt's section.
Yeah. Hotspot's working well. America's a first world country, right?
All right, Matt, does this look familiar?
It does. Okay, cool. So I think I chatted about this. We were chatting about how schema enforcement's preventing bad appends. We had this pandas data frame. It has a mismatched schema from the existing schema of the Delta table. When we try to append it, we're getting this value error schema of data does not match table schema, which is great. This helps keep our data pristine. We don't have any such checks if we're using Data Lake. Okay. these are constraints. Let's chat about constraints. So let's suppose we have a delta table with 2 columns, name and age. And then let's add a constraint to the table. So we are going to add this constraint with this alter.add constraint syntax. We'll name the constraint age GT0, and then we're just going to add a little SQL predicate that specifies the constraint. And in this case, its age is greater than 0. So this means that you can't append negative ages to this table. So let's create a pandas data frame with 1 row of data that satisfies the constraint and another that does not. So in this case, we have this individual Luis with an age of -45. And because we have this constraint in our table, we're saying, hey, we don't want to let this data be appended. So now we run this write Delta Lake command as we have in the past, and we set the save mode to append, and we can see that we're going to get this error, and it says invariant violation, check or invariant, age is greater than 0, violated by the value in the row, Luis -45. So this is wonderful. We can see that that bad data isn't appended to our table, and this is really nice because it kind of keeps the data clean in our table. Now, one thing I will note about constraints is that a transaction either completes fully or does not complete at all. So in this case, there's 2 rows that we tried to append. One was Tom 65, Luis -45. The Tom 65, even though it satisfies the constraint, does not get appended. This entire transaction is rejected. Okay. I'm going to skip this, but this kind of just shows how you can overwrite a partition of a Delta table with the Pandas engine. And that's pretty cool because that doesn't exist for, like, let's say you're using a Parquet Lake with Pandas. You don't have that functionality. Okay, I'm just going to fly through this last slide, which talks about how we can make a Pandas query 20x faster with Delta Lake compared to a CSV file. So I ran this query on my local machine. This is a 5 gig data set that has 9 columns of data. So it has 100 million rows of data. You might have seen this data set before. It is the H2O group by data set. So in that section 2, we can see this running the query of the data with the CSV file. So we need to specify that use calls parameter when we're querying the CSV file. Otherwise, Pandas blows up, even though my machine has 64 gigs of RAM, but it still can't handle this. So then we're running a query for all the values where ID1 is equal to ID016. So that's exactly 1% of the data. And then we're running this group by aggregation. So this takes 20.6 seconds on my machine, and it's kind of slow. So let's see how we can make this faster with Delta Lake. So what we do with our Delta table is we z-order the data on that ID1 column. Now, what that's going to do, it's going to co-locate similar data in similar files. So rather than having all of the data stored in one file, the Delta table is going to have the data stored in many files. And when you z-order the data, it's going to have the similar data in similar files. And then there's going to be a Delta Lake transaction log that contains the file level metadata. So when we run this query, the engine can just simply skip data skip files that don't contain any relevant data for the query. So the syntax is a little bit more onerous. Basically, what we're doing is we're reading in the Delta table. We're specifying some predicates using this PyArrow syntax. But at the end of the day, we are running the same group by filtering and then group by query aggregation that we ran before. And we can see that this runs in under 1 second. So we have a query. It runs 20x faster with Delta Lake, thanks to file skipping and z-ordering, and the Parquet file format is obviously helps too compared to CSV. So for Pandas users, you can get much better query time with Delta Lake, especially when you can leverage file skipping. I think that's it for me. Yep, that's it for me.
Awesome. Thanks so much, Matt. All right, I'm just going to navigate to TD's section. Perfect.
Thank you. Thank you, Carly. Thank you, everyone. Those were really informative sections on how to use Delta in various different ways and what's the new cool stuff that is coming, like type widening and stuff. Let me actually expand that view a little bit more, and because we have a bit of updates to talk that we can talk about regarding where Delta is heading. So on the horizon, there is a Delta 4.0, which brings a lot of these features like type widening that you heard about. And the exciting update is that Delta 4 will be on Spark 4.0. And Spark 4 is currently undergoing voting on a Spark 4.0 preview release, which is very exciting because all the Spark changes that we did in order to make all these cool new features in Delta work, like type widening and stuff, this will be our first chance to actually try them out. So while the Spark 4.0 preview is being voted on in the Spark community, in the Delta community, we also have started testing out the Spark 4.0 preview release candidates and stuff. So our plan is that as soon as Spark 4.0 preview is released, we want to release a Delta 4.0 preview so that the community can try out all these new cool features like type widening and stuff. And so the testing is in progress, and we're hoping that by early June, both Spark 4.0 preview will be out, and therefore Delta 4.0 preview will also be out. Now, to recap, I've covered this in my last meetup talk. The cool features that are very much in progress that are worth previewing are type widening, which we have heard already in quite a lot of detail. But it is in the same theme as another feature called variant types. Basically, how do you evolve the schema of the table in a more flexible manner without rewriting the entire table? So with type widening, you're getting automatic type upcasting on read. With variant types, which is another cool feature that is in Spark right now, but we want to make it work nicely with Delta tables, is an even more flexible schema evolution where not just type upcasting from int to long, but you want to be able to do any kind of flexible dynamic typing on data. Like you have data, let's say you have semi-structured data, JSON coming in, sometimes a particular field is a string, sometimes it becomes an integer, etc. And dynamically you want to, at read time, you want to read it as either a string or want to force it to be casted to an int. That kind of dynamic capabilities will be available with variant types. Again, I will not go into the details here. The details will be covered in the Delta 4.0 preview and maybe future meetup talks and stuff. But I think this is going to be a huge focus of 4.0 preview is how do you make schema evolution even more flexible than what it was. And this is like really cutting edge. No other format has this kind of, no other open source format has this kind of flexibility and stuff. The other architectural change we are doing in Delta is this thing called manage commits. I've talked about it in a little bit detail in the previous meetup talk, but to summarize, it is basically right now the Delta protocol is tied to the file system, and it depends on file system guarantees to provide the ACID guarantees. We want to expand that capability to allow other kind of commit owners like catalogs, make DynamoDB, which is already supported, but make it a more formal thing where it can give more stricter guarantees, or catalog-based commits and stuff like that. Please look at my previous meetup talk. It is a very cool feature. It's a fundamental architectural change for Delta. And then another architectural change in Spark itself is called Spark Connect, where the Spark itself can be run in a server client mode, where the client, your application Spark code is running in a client talking to a remote Spark server. So you don't have to, which provides a lot of nice benefits and isolation and failure isolation between your application code and the server code and stuff. Again, I've talked about the previous talk, but we want to add support for Delta Connect, for Delta in the Spark Connect architecture. Again, a fundamental change. all of this justifies having a major version release like Delta 4. So stay tuned. Lots of exciting stuff coming up. Back to you, Carly.
Excellent. Awesome. We can now transition into some Q&A with the community here. All right. Oh, I guess we can leave this up while we're doing questions. Okay. This is a question for TD, Matt, and Johan. Or actually, pardon me, this is a question for Matt. Would you recommend optimize and Z ordering together for a better performance?
Yes. So optimize is to compact small files. Z order is to co-locate similar data in similar files. So there's a bunch of actually different tactics to improve the query speeds of a Delta table. So you can optimize for small file compaction. You can do hive style partitioning. You can Z order. You can do Z ordering in conjunction with hive style partitioning, or you can do the new liquid clustering. So it's actually kind of like that's a long answer, but definitely recommend checking out the blog on Z ordering, hive style partitioning. I think the future is mainly liquid. That's going to be the easier way to deal with this on a go forward basis. Hive style partitioning has lots of drawbacks, of course. But yes, if you're using Z ordering, definitely optimize as well, because you don't want excessively small files.
Wait, just to be clear, when you run optimize Z order, your files will be Z ordered as well as compacted. So you don't need to run optimize for compaction and Z order, optimize Z order separately. It's one or the other. So if you know exactly what columns to order your data by, or would you cluster your data by, then you run optimize Z order on those columns. If you don't know, or it doesn't matter whether the clustering doesn't matter, you just want to compact your files, then just run optimize compact. Just optimize compaction.
Awesome. Great. And while we're talking about Z ordering, to make Delta tables Z ordered, are there any explicit properties we need to set, or is it created by default with setting?
That's a wonderful question. So you need to Z order a table based on columns. You should Z order tables based on the columns that you're querying most often, like filtering queries and stuff like that. Z ordering is kind of an interesting algorithm. So like you can specify multiple columns, and yeah, it's kind of going to be hard to explain this right now. But basically, it's a good set of trade-offs for multiple different columns, but the effectiveness of Z ordering kind of decreases as you add more columns. So it's kind of this balancing act. I'll drop in the blog post in the chat that kind of discusses this in more detail.
Yeah. I think that's where, based on these shortcomings of Z order, as well as hive style partitioning, that's how the liquid clustering was designed, which chooses a different, not the Z order spatial curve, but a Hilbert spatial curve, which has much better properties, as well as it allows you to not have to, so with optimize Z order, for every time you run the command optimize Z order, you have to specify the columns to Z order by. With liquid clustering, if you create the table by saying create table, blah, 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 cluster by these columns, then you don't need to specify those columns every time you run the optimize command. So you can just specify those column once and then run optimize. It will always use those columns. You can obviously change the columns using an alter table command. So those are the usability and also performance advantages that comes with liquid clustering.
Excellent. Awesome. Another question here from Hamid. Hamid would like you to compare added schema evolution capabilities with Avro schema evolution capabilities. What is extra here?
All right. So I'm not super familiar with the capabilities in Avro.
Yeah, neither am I off the top of my like the basic things like adding columns and stuff, Avro and Delta, we have been always been equivalent and stuff. But Avro, I doubt really supports things like variant types and stuff where Delta is going towards. In terms of whether type widening is supported in Avro, I guess it depends on the reader. If there's a fundamental architectural difference. Avro is a row-based format. So it you can have a single Avro file or a single Avro row. Now it's all depends on the reader of those Avro files to really reconcile that, oh, some Avro files or rows are in format 1, another set of them are in format 2. So how do you reconcile them and stuff? So yes, it is theoretically possible to do things like type widening, etc., using Avro, but with Delta, it will be baked into the protocol of the Delta, which is a table-wide protocol, not a single file or a single row format.
Yeah,
Hopefully that gives.
let me chime in there, like kind of just rephrase or what TD, or not rephrase, but just kind of reiterate what TD's saying with different words. So basically, Avro, JSON, CSV, Parquet, those are file formats. And then like Iceberg, Hootie, Delta Lake are lakehouse storage systems or like open table formats. So anytime you're kind of like comparing like a lakehouse storage system and a file format, you're already kind of like a little in apples oranges comparison territory. But yes, in addition to that, there's like row-based file formats and column-based file formats. So like Parquet and ORC are column-based file formats, and JSON, CSV, Avro are row-based file formats. So there's kind of like a lot of differences going on there with that comparison.
Much better than what he said. Thank you, Matt.
Awesome. Here's a deletion vector question. When we enable deletion vectors and auto compact, both for the tables, will bin files be unpacked and created into compacted files?
Good question. So let me try this question, and Johan, correct me if I'm wrong, or if you know any better. But auto compact today does not automatically compact bin files, right? The deletion vectors right now, that is an improvement that can be made. However, the optimize command, which does the compaction, Z-order and stuff, that will take care of deletion vector bin files and stuff by merging it in them. Merging it, like rewriting the files and removing the deletion vector bin files and stuff.
And essentially, any file that gets rewritten by any command, if it had deletion vectors before, these are going to be removed because the data is going to be, the deletion vectors are going to be applied to the data that's being read. And when writing out the new files, then these won't have deletion vectors anymore.
Yeah, but I think a question boils down to, it's a question of the auto compaction command, what files it chooses to rewrite. I think it is very conservative in choosing files. So a user should not expect that if you have auto compact enabled, all the files will be eventually rewritten. That is probably not true. But if you have optimize enabled and you're continuously optimizing your table, it will probably get compacted. The deletion vectors will get removed much more.
Right, and there's the reorg table command purge that can allow you then to explicitly ask to remove the deletion vectors.
Yes, good, thank you.
Awesome, thank you very much. Another question: will reorg have conflicts with write operations like the merge command?
Yes, I believe.
Yes.
Perfect. Okay. When should we use the optimize write and write repartition enabled? Could you please share some example cases?
Right, repartition enabled. So for the optimized write, the best way to think about optimized write in auto compaction is that at the time of writing the data, if you want to avoid creating too small files or maintain a table state where there are not a lot of small files continuously being added or present, these are the two independent features that you can enable independently. Optimized write ensures that the write operation itself does not produce small files. It produces larger files to begin with. But will it be the most optimal size large files? No. It just avoids like small files like 1 MB, 2 MB, 10 MB, that kind of small files. So it'll try to pack it to like larger 100 MB sized files and stuff in the new data that is being written out. Auto compaction, while the operation is going on, in the background, the auto compaction takes already written out small files and tries to compact them into slightly larger files, like 100 MB level, that kind of level of files. I mean, I'm being particularly hazy about the numbers because it is all a heuristic, and these numbers are subject to change as we tune these sort of what each operation does. So if you enable both of them, then out of the box, your table will have lot less very small files, but it comes at a cost as well, because if you do these sort of operations, that means you're doing more work at the time of writing. It will slow down writes a little bit, but what the outcome of that is that at any point of time, your table will be much better for reads, because there will be much less files, small files out of the box, even before you run optimize and stuff.
Excellent. We have 1 minute, so I do want to just do the small plug that please join our Slack, the Delta Lake Slack. It's a great place to put your Delta Lake questions. The community will answer those. Also, follow us on LinkedIn, follow us on X. We're always sharing our latest blog posts, documentation. It's a great way to stay connected to Delta Lake. And also check out what's coming in the Delta Lake roadmap, and you may find some areas where you can also contribute to.
Yeah, sorry we couldn't get all the questions, everybody, but make sure you just copy paste these into the questions channel of our Slack so we can get to all these.
Definitely.
Thank you for all the wonderful questions.
Yeah, these are awesome questions. And we do these some pretty regularly, so make sure you keep an eye out for our next Delta Lake Community Meetup. We also have Data and AI Summit coming June 10th to the 13th. If you have not registered, we highly recommend attending. You'll find out what's coming with Delta Lake. We have some awesome sessions there. I think we have about 20. So feel free to check out what's going on at Data and AI Summit and register. We'd love to see you there. All right, and we're at the hour. Thank you so much to our wonderful panelists today. The great speakers, awesome presentations, and a super engaging audience. Thank you for the awesome questions. We will reconvene in Slack. We hope to see you there. Thank you, everyone.
Thank you, everyone.
Bye.
Thank you. Bye-bye.